This is Lily, and I will be discussing application problems 4 and 5. So question 4 is about a spirogram, which is used to record volume of air in a person's lung as a function of time, and we're given that v of t is equal to 3 plus 0.05 sine of 160 pi of t minus pi over 2. Part A asks to compute the volume at different points 0, 1 over 320, 1 over 160, and 1 over 80. So that you just plug into the equation and solve. So we get 2.95 for v of 0, 3 for v of 1 over 320, 3.05 for 1 over 160, and 2.95 for 1 over 80. Part B asks what the maximum lung volume is. So to do this, we take the derivative of v of t, and we end up getting 8 pi cosine of 160 pi of t minus pi over 2. And to find the max, we set the equation equal to 0. So we solve this, we plug it into the calculator because we have to do the cosine inverse, and we end up getting t is equal to 160. We plug that in back into the volume equation, and we've already solved that. We get v of 1 over 160 is equal to 3.05, which is the max lung volume. Continuing on, part C asks to find a formula for the rate of flow of air into the lungs at time t. So this, you just take the derivative, which we already solved in part B. So the rate of flow formula is 8 pi cosine of 160 pi of t minus pi over 2. Part C asks to find the maximum rate of flow during inspiration. So what we do is we set the equation equal to 1 to solve for t. We go through that and we get t is equal to 1 over 320. We then plug that into the rate of flow formula, the v prime. We solve that and we get 8 pi. So that means that the max rate, or the peak inspiratory flow, is 8 pi units. And the next part asks to find the average rate of flow between t equals 0 and t equals 160. So we know that there are 80 inspirations in 1 minute due to the period of the function, and so the total air inspired in 1 minute is v of 1 over 160 minus v of 0 equals 3 plus 0.05 sine of pi over 2 minus 3 plus 0.05 sine of negative pi over 2, which is equal to 3 plus 0.05 minus 3 plus 0.05, or 0.1. So then we find the minute volume, so 0.1 times 80, which is 8 units. To find the average, we multiply that by 2, so we know that the average rate is 16 units. Question 5 is about Native Hawaiians who start off with a population of 5,000, and a sailor brings a disease with an infection rate of k equals 0.25. We know that the spread of an epidemic is modeled by dy dt equals k times 1 minus y over n times y. Part A asks to write an equation for the number of natives who remain uninfected. So we know that n equals 5,000 and k equals 0.25, so we can plug this into the previous equation and get dy over dt equals 0.25 times 1 minus y over 5,000 times y. Simplifying that, we get dy dt equals 5,000 minus y times y all over 20,000. So next we separate the variables and integrate. So we want to combine all like terms, and we end up getting dy over 5,000 minus y times y equals dt over 20,000. We take the integral of both sides, and we end up getting 1 over 5,000 ln of y over y minus 5,000 equals t over 20,000 plus c. Then we end up solving for c, and we get 1 over 5,000 ln of y over y minus 5,000 equals t over 20,000 plus 1 over 5,000 ln of 4,999. And now we solve for y, and you can see my work there where we're solving for y. And we end up getting to 1 over 5,000 times the ln of y over 4,999 over times y minus 5,000 equals t, and we know that using ln and e properties, we can take the e of both sides and then multiply both sides by 4,999, and we end up getting y over y minus 5,000 equals 4,999 e to the t over 4. Then simplifying that, we end up getting y equals 24,995,000 over 499 plus e to the 0.25t, so that's our equation for the number of natives who remain uninfected. Moving on to the next part, it asks how many are uninfected after 15, 25, and 50 days. So this part is pretty simple. We just plug in 15, 25, and 50 into the equation that we previously derived. So at 15 days, 4,958 people are uninfected. At 25 days, 4,531 people are uninfected. And at 50 days, 91 people are uninfected. Then part C asks when will the maximum infection rate occur? So we take T max is equal to the ln of n minus 1 over k. We just plug in what we know is n equals 5,000 and k equals 0.25. So simplifying that, we end up getting the ln of 4,999 over 0.25, or 8.5169 over 0.25, which is about equal to 34.0679. So the maximum infection rate occurs at about 34 days.
This is Meti, and I'm going to be explaining problems 6 through 8. And so for problem 6, I wanted to start off by making sure all my units were the same. And since the problem states that P of T denotes the number of grams of radium-226, I converted the constant rate of 3 milligrams to be 0.003 grams. And so to find the initial value problem, I first wanted to find the equation for the rate, which was going to be whatever is being added each year minus whatever is decaying. And so I found that to be the constant rate of 0.003 minus the decay rate 0.00043 times the P of T. And so I manipulated that into the first order form so that I could solve the initial value problem. And so I got that the rate or derivative of P of T plus 0.00043 P of T is equal to 0.003. And because the 0.00043 is in front of the P of T, that's going to be A of T. And then because the 0.003 is on the right hand of the equation, that's going to be B of T. And so from there, I went to find capital A of T, which is the integral of AT, and which is, for this equation, is the integral of 0.00043 dt. And I found that that is equal to 0.00043 of t. And from there, I found the integrating factor, which is e to the power of capital A of t, which for this equation would be e to the power of 0.00043t, which we found in the last part. And then from there, I found the integral of the integrating factor times b of t dt, which for this equation is going to be integral of e to the power of 0.00043t times b of t, which is just 0.003 dt. And so from there, I was able to take the constant out of the integral, so I got 0.003 integral of e to the power of 0.00043t. And I used u substitution to solve the integral, so that I set u to be 0.00043t, and so du would be 0.00043 dt, and dt would be equal to 1 over 0.00043 du. So then from there, I took out 1 over 0.00043 out of the integral since it's a constant, and I was left with 0.003 times 1 over 0.00043 multiplied by the integral of e of u du, which is just going to be e of u. And then since we set u to be equal to 0.00043t, I just plugged that back in. And so then I got that 0.003 over 0.00043 e to the power of 0.00043t plus c. So then from there, I did the next part of the initial value problem, which is that P of T is equal to e to the negative A of T times the integral of e to the AT times BT dt, which we just solved. And so for negative, since a of t is 0.0043t, negative a of t is negative 0.00043t. And so p of t is equal to e to the negative 0.00043t multiplied by the integral that we solved earlier, which is 0.003 divided by 0.00043 times e to the power of 0.00043t plus c. And from there, I FOILed e to the power of negative 0.00043t, and I got that it is equal to 0.003 divided by 0.0043 times e to the 0.00043t divided by e to the 0.00043t plus c times e to the negative 0.00043t. And since the e to the 0.00043t at the top, and there's one at the top and the bottom, that's just equal to 1. So the general form of the equation will be p of t is equal to 0.003 over 0.00043 plus c e to the negative 0.00043t. And since we know that the container is initially empty, that means p of 0 is 0. So we can set up that equation to find c. So we get that 0 is equal to 0.003 over 0.00043 plus ce to the negative 0.00043t. 0, since t is equal to 0. And so since it's e to the power of 0, that's just 1. So then we get that c is equal to negative 0.003 divided by 0.00043. And so then we just plug that back as c into our equation, and we get that our final equation is p of t is equal to 0.003 divided by 0.00043 minus 0.003 divided by 0.00043 e to the negative 0.00043t. Last part, which is what is the limit of the amount of radium-226 in the container when t tends to infinity. I set it up like this as limit of t approaches infinity of our equation that we just found in the last part. And since 0.003 divided by 0.00043 is a constant, we can take that out of the limit and just solve the limit of as t approaches infinity of 0.003 divided by 0.00043 times e to the negative 0.00043t, which is just known as 1 over e 0.00043t. So to find that limit, I took out 0.003 over 0.00043 again, since that is also constant, and I was just going to multiply it with the limit of 1 over e to the 0.00043t as t approaches infinity. And so if t approaches infinity, we are left with 1 over e to the power of infinity, which is just 0. So when we put that all together, it would be that the limit is equal to 0.003 over 0.00043 minus 0.003 over 0.0043 times 0, that part would just be equal to 0. So then we're just left with 0.003 over 0.00043, which can be simplified to 6.977. And so to interpret that, I got that as time infinitely increases, the amount of radium-226 in the container remains at 6.977 grams. 7, since the equation was already given to find C of 25, C of 40, and C of 50, I just plugged in each of those values as t and solved using a calculator. So I got that C of 25 is equal to 370 parts per million, and C of 40 is equal to 418 parts per million, and C of 50 is equal to 460 parts per million. And to find C prime of 50.2, I knew that I first had to find C prime of t, which is the derivative of the original equation. And so I knew that since all these values are being added together, you can just find the derivative of each separate one and add it together. And the derivative of 0.4t squared, you would bring down the 2 and then subtract t to the power of 2 minus 1, which is just 1. So you get 0.04 times 2t, which is 0.08t, plus the derivative of 0.6t, which is just 0.6 because it's 1 times 0.6, t to the power of 1 minus 1, which is 0. And then for the derivative of 330, since it's just a value and there's no variable, it would just be 0. And the derivative of 7.5 sine 2 pi t, you can use the chain rule. And so first you start by doing the derivative of 7.5 sine 2 pi t, which you get 7.5 cosine 2 pi t, and then you have to do the derivative of the inside since it's a chain, and so you get the derivative of 2 pi t, which is just 2 pi. So then we're left that c prime of t is equal to 0.08t plus 0.6 plus 7.5 cosine 2 pi t times 2 pi. And so from there, I just plugged in 50.2 as t, and I got that c prime of 50.2 is equal to 19.178. And since the c prime of t tells us the rate of change, I interpreted c prime 50.2 to be the rate of change in the carbon dioxide levels in barrows 50.2 years after 1970, which was t of 0, which is going to be the year of 2020, and that it's expected to be 19.178 parts per million, which is the rate of change. And I interpreted the parts of the equation to be that the sine function is used in an effort to model the variations, like how it cycles in a year in terms of weathers and seasons and how that can affect carbon dioxide levels. And then the quadratic function part models the increase in carbon dioxide levels as time goes on. So for problem 8, since it tells you to use Euler's method with h equals to 0.2 to approximate t equals 1.4, I first wrote down everything that was given, which was the equation for the rate of change and the h, which is 0.2, and that we are given that y of 0 equals 10. So Euler's method is that for y1, it would be that y1 is equal to y0 plus the rate times h. And so for this particular problem, it would be that y of 1 is equal to y of 0 plus the equation that we're given, which is 0.02 times 100 minus the square root of y0 times 0.2. And so for y0, we know that it's 10, so that's just going to be y of 0. And then for the first iteration, which is y of 0.2, we plug in y of 0, which is 10, so we get 10 plus 0.002 times 100 minus root 10 times 0.2, and we get 10.387. And then we do the second iteration, we plug in y of 0.2 into that part, so then we get 10.387 plus 0.002 times 100 minus root 10.3.87 times 0.2, and I got 10.774. And so I kept doing that till the 7th iteration and plugging in the previous value for the initial y, and I got to the 7th iteration, which would be y of 1.4, and so I got 12.706, which can be rounded up to 13. So I just said that when t equals 14, there are about 13 species.